join this session on GIS in R, where I'll introduce to you to R if you R and RStudio if this is the first time for you to work with R, but also we'll look at spatial data packages in R and R spatial data analysis and R cartography. So depending on your interest, I hope you find this session important. I know with people joining from different parts of the world. So I'm Dickson Mbeya. I am a cartographer and biodiversity informatician based in Malawi, and I have an MSc in biodiversity informatics and a BSc in earth sciences. I've been working in GIS and cartography or remote sensing field for more than 7 years, and have been a GIS analyst and spatial assessment lead in multiple projects. So my interest is to apply GIS and remote sensing in addressing different problems. So you can just type in the chat your name and where you have joined the session from, so that you get to know who is here. So a few rules for us throughout this session is that let's make sure that we switch off our video and switch off our mic when not speaking, and ensure that everyone feels respected, and you can post your questions in the chat and I'll attend to them during the break time and a Q&A session. But if you can't hear me, or there's something else that you want me to sort out as we are progressing, please feel free to unmute and interrupt me. So I'll start by giving a brief introduction to GIS, and then we'll look at R and RStudio, and then transition into introduction to R, and then finalize by processing or working with GIS data in R. So GIS stands for Geographic Information System. It is a computerized-based system or computer-based system for capturing, preparing, storing, maintaining, manipulating, analyzing, and presenting data. And it has 5 components. Of course, others present it in 4 components. So there's the software, there's the hardware. So the hardware is a computer or your mobile phone. Then there's data. There's methods, which are procedures, which are the guidelines on how you process data, how you manipulate data, how you visualize data. And then there's people. So people are those that are working with data, with GIS data, using the software to manipulate, visualize, and present different information products out of spatial data. So software can be any desktop-based software, for instance, or cloud-based platform. So you can talk of QGIS or ArcMap, Supermap, iDesktopX, GrassGIS, etc. This guy, known as Roger Tomlinson, is considered to be the father of GIS, and he said that no GIS can be a success without the right people involved. A real-world GIS is actually a complex system of interrelated parts, and at the center of this is a smart person who understands the whole. Just to emphasize that you are the main component of a GIS. What can you do with GIS? You can use GIS to capture data. You can use GIS to store data. You can use GIS to analyze data. You can use GIS to present data. You can source data from existing hard copy maps, and you can digitize the hard copy maps, and then store data in a relational database, and then you can process data, analyze, for instance, find the closest facility to a particular location, and then come up with information products in form of maps, charts, graphs, web apps, web maps, etc. So when talking of GIS, we'll now talk about GIS data. GIS data basically comes in two parts, as spatial data and attribute data. So spatial data, you are talking about, or you're answering the question of where, and then attribute is you ask a question of what. So anything on Earth exists somewhere, and the first thing is, where does an object reside on Earth? And that is spatial data or location. So you can capture that data using XY coordinates, or you can capture that data using address, or you can capture that data using or in form of latitudes and longitudes. So it's just a form of the projected coordinate system or geographic coordinate system, depending on the system that you're using to capture location. So it can be in X and Y coordinates when you're looking at projected coordinate system, or in latitudes and longitudes, can be degrees or decimal degrees when you are looking at geographic coordinate systems. Whereas describing the non-location information of an object, then you're talking about attribute data. So a city exists somewhere, and when we get the coordinates of the location of the city, that is spatial data. But the name of that city, the ID of the city, the population of the city, that is attribute data. That's non-location data. So here I'm giving an example of a map of Malawi, which is a country located in Southern Africa, and you see that then an attribute table that has attributes associated with the polygon of the country Malawi. And then you can see different attributes in forms of columns, and each column is a specific attribute describing the location, describing the object of interest, which is Malawi. So when you're working with data in GIS, there are two basic or major data models on how you can present data. So data can be represented in form of vector, or you can represent it in form of raster. So a vector data model, which is a model, is just a representation of reality. And a vector data model is used to define objects with this distinct boundaries, such as rivers or a country boundaries, city locations, etc. And you present data in a vector data model using points, lines, or polygon. So a point can be defined by a single XY coordinate location, whereas a line would be defined by two or more locations that are connected with lines. And a polygon defined using multiple locations that are connected and closed. Like we have a number of points here, and each point has its own latitude, longitude coordinate. And we have two lines here, and each line has 1, 2, 3, 4, 5. So this line has 5 locations but connected. This one has 4 locations connected, and you have polygons which are defined using multiple locations that are connected but also closed. You can also talk of GIS data in form of raster data model, or presented in form of raster data model, when you use to define objects or phenomena that doesn't have distinct boundaries, such as temperature or elevation. So at every point on Earth, there is a value. So in raster data model, a raster data model is made up of equally sized cells that are arranged in rows and columns, and each cell in a raster stores a value. So what I'm showing here is a map of a country, Malawi, a digital elevation model, or a digital elevation surface, a digital elevation model for Malawi that represents elevation, which is the height above sea level. And each of the cells has a value. So the values that you see here zoomed into this particular point in Malawi, these are values representing elevation. So height above sea level, so whether it's 101 meters above sea level, 573 meters above sea level, 800 meters above sea level. raster data model can also be used to represent district phenomena. For instance, you map land cover of an area from remote sensing imagery, and you get classifications or land cover map for a country. Like this is a land cover map for Malawi from European Space Agency 2024 land cover, global land cover. And then district rasters will have values that represent a code for a particular category. So you have a number of categories here. What is blue on this on this map is water body, and what is green is tree cover. And in raster data model, and when you are representing district phenomena, you have different maybe codes. So a code 90 can represent trees, or a code 10 can represent water in a raster data model, where you are representing data, you are representing district phenomena. Let's also talk about layers. That when you are working with GIS data, you model the world into different layers. So you have, in the real world, you would have a city with different components. You have water bodies, you have buildings, you have trees, you have parks, you have elevation, you have boundaries and demographics, transportation system, etc. In GIS, you would break down the real world into different layers, and then you would have points representing specific locations within a city, and you have lines representing transportation network, you have boundaries, you would have landmarks, you'd have a layer of water features, a layer of elevation, and then you have a base imagery for a particular city. So it just combines the layers of data representing real-world locations and entities. How is GIS applied? GIS can be applied in many things. In 2020, we had coronavirus, COVID-19, and Johns Hopkins University developed a dashboard that was used to visualize the spread of the virus. And that was one application of GIS. That was built on GIS. You can create stories in ArcGIS. There are story maps, and you can create story maps to present information to the public. You can use GIS in hydraulic modeling. For instance, you generate a river catchment area and visualize it for hydrological applications. There are multiple ways on how you can use GIS. The limit is dependent on the user. So just to clear this, a GIS is not a GPS, and a scanned map in a computer is not a GIS. We've defined what a GIS is, and we have looked at different components, and those components are what forms a GIS, and anything less than that is not a GIS. So what is R? R is a language and an environment for statistical computing and graphics. What we try to achieve in this session is to go beyond statistics by looking at R, transforming our R environment into a GIS tool. And it compiles or runs on a wide variety of Unix platforms, Windows, macOS, and for us to work with R better, we use the integrated development environment known as RStudio, which is a flexible and multifunctional open source IDE. And it is extensively used as a graphical front end to work with R. And that's what we'll be using during this session. So this is just, this shows the different components of RStudio. If you went through the resources that I shared before, you by now should be familiar with this interface. So this is an interface for RStudio where you have the source pane, and this is where you write your code, and then you have the console. This is where your code is executed, and you can see the output, but also the output pane this side. If you're processing data and you producing maps, graphs, you would see them in the output pane. Environments, you create objects, you'll be able to see them in this environment pane. So why should we use R for GIS and not just be limited to desktop GIS? R is a great resource for data analysis. The multiple things that you are able to do in desktop GIS, but we can also do them in R. Some people may have been introduced to R, and they may not be familiar with desktop GIS, and you can continue working in R and be able to work with spatial data, process data, and visualize data, and even apply machine learning models and translate your data into information products. And R has many packages that can be used for geospatial analysis. We'll look at some major ones during this session. And it's good for reproducibility of processing workflows. If I do an analysis and I get the results, for somebody to repeat the same analysis, if I write an R code, I can just send them the code and then share with them the data set, and they can reproduce the same thing. Whereas in desktop GIS, even though you can have similar instructions, but there will still be some differences in terms of redoing the same thing, and the process would be really time consuming. And there is a large community support that supports R language. So here I'm just showing examples of outputs that are made in R, and you have this separation map of Africa, and to be able to see that this map is produced in R. So you have all the map elements of interest in there, and you can put it in a map application or in a report, etc. And down there, you're seeing the elevation for Mount Kilimanjaro. So just to show you that you can work with both vector data as the map at the top, you can work also with raster data as shown here. It's time for hands-on now. We've done enough introduction. I hope that if you are new to R, you are new to QGIS, not to QGIS, but to GIS, I mean, you have now an understanding what GIS is and the reasons why we are going to use R for GIS. Thank you. I'll be transitioning now. We'll be transitioning now to RStudio for us to start hands-on. In case there is any question, please feel free to post in the chat. Okay, so you can go ahead to open your RStudio or to start your RStudio. Okay, so what I'll do now is I will attach the code that we use for the first introduction. and you can download it. So I'll attach it in the chat. It's 8 KB, small file. So you can download that R script and you open it in RStudio. So I've attached it in the chat, posted it in there. You can download it in a minute, then you'll be able to open it in RStudio and proceed. Yeah, so the recording will be sent after the session, probably within the week. So you don't need to have or to pay for R or RStudio. It's open source. Okay, so if you haven't downloaded R or RStudio, then it will be difficult for you to follow along, but you can just follow what is going to be we're going to demonstrate. But if you have to follow along the presentation, it's important that you open your R and RStudio, and you open your RStudio, because by now, from the resources that I had shared, you should have already known how to download, where to download, and how to connect R to RStudio, so that in this session, we just go into actual business of working in RStudio. So thank you so much. Yeah, the slides will be shared along with the recording later. Okay, so let's proceed. When you open your RStudio, you will okay, just stop this one after. You have a blank let me studio. Okay, so this is how your RStudio is going to look when you just open it for the first time. You only have the console here, and then you have the environment pane, but you can always minimize or maximize these windows. The same here. Okay, and then you open your source pane. So what I would want us to do is okay. So this is where we were before. Then we just maximize this window so that we have the source pane and then the console down here. In the console, I can type 1 plus 2 and hit enter, and it gives me 3. 2 plus 3, hit enter, it gives me 4. 2 minus 1, hit enter on my keyboard, it gives me 1. So, but working in the console, when it comes to documenting your code, it's something that would be difficult. So the best thing is for you to work in the source pane. Type my name there, hit enter, prints out my name. So the file that you have downloaded, you can just go on to open it, go on file, and then open file, or Control O. Then navigate to where you have your file kept. So I have mine in this folder. Then I hit open, and that file loads in my RStudio. So if you are struggling, please feel free to unmute and interrupt me if you need any assistance to follow along the session. So when you open that, you open the code, you will see that there are a number of lines of code in here up to 218. Don't be scared with the number of lines. If this is the first time for you to work with R, so there are things. The first thing that I'll mention is the first. Thank you. I'll slow down so that we can follow along without issues. That's noted. So I hope we've managed to open R and to open RStudio and to load the script that I've shared in RStudio. So when you're working in R, you can comment out your code, or you can write comments. When you write a comment, is something that is not going to be executed by R. So in a programming language, a programming language is just an instruction that you give a computer to do. So you write an instruction for a computer, and the computer follows that instruction. For instance, here I wrote that my computer should add 1 and 2, and it gives me 3. So this is a language, and then I write this, and the computer understands this as a summation, this as an addition operator, and it gives me an output. So I tell a computer, so when it's on, it was doing nothing, just ready to accept anything that I would give it. So I would say type Malawi. So I type Malawi and press enter, and I'm telling the computer that can you display Malawi, and it does. Okay. So it's just an instruction that I'm giving a computer. Now, if I want something not to be executed, so I say 1 plus 2. Let's see what's going to happen. Okay, so I put a hashtag, okay, and then 1 plus 2, and you see that it doesn't give me anything. But if I do 1 plus 2, it gives me 3. But if I start my code, or my line of code with the hashtag, it doesn't give me any output. The reason is the hash symbol, or the pound symbol, is used to comment a code, a line of code. Also, it's a comment. It's anything that is after this symbol is not going to be executed. So execution is the processing of the line of code. It's not going to be executed. So whatsoever is in this code, whatsoever is after any hashtag is not going to be executed. So line number 1, you have a hashtag, and then there's these multiple equal signs, and then there's another hashtag at the end. This is not going to be executed. Line number 2, number 3, 4, 5, 6, 8, 7, 8, 9. All these will not be executed. But line number 11, line number 12 is empty. Line number 13, for 15, these are going to be executed, and we'll be able to see an output. So what are these used for? These comments are used to describe to describe your code. Here there are multiple comments that are just some of them. Most of them are obvious things in a real when you are writing, you will not comment some of the lines of code that I've commented, but this is just for us to be able to follow what is going on. But if you write a code today is 23rd March 2025, and imagine you are performing a certain spatial analysis that is complex and long, and then there are maybe hundreds of lines of code. You would want to, uh, if you come back to the same code next year or 2 years later, you'd want to remember what you were doing at that time. So humans are not good at at remembering everything. So that's why we write comments, so that next time we come back to the code, we'll be able to remember what we were doing. Or if you want to send that to someone, and they should be able to follow along what you were doing, for them to repeat the same things that you had done. Like what I've done here, I've commented out different sections of the code, the script, just for you to be able to follow what is happening. Now, the first thing that we'll do is we'll set a working directory. So a directory is just a folder on your computer, and this folder is where you are saving your script, and that's where you have your data set. So before this session, I sent through the email the data set that we're going to use for this session, and that data set is a zipped file GIS in R. So make sure you download it and extract it and place it in a folder or a location where you will be saving your script. So to set a working directory, you use a setwd base function of R. So setwd is a short form of set working directory. For me, I have my working directory in the documents of the user Dickson Mbeya and in the C drive. So this is just a path, line number 11, a path to my folder. And there's a folder in this directory, March 23. And this is my working directory. This is a folder. It's inside the folder RGIS, inside the folder seminars. And this is inside the documents library. So what you do is you need to change this to your directory. So everything that is within these double quotes, you're supposed to change this to the path to our directory. How do you do it? The easier way of doing it, so to avoid running into errors, is just open the folder where you're keeping your stuff. So like for me, I'm using the File Explorer, I'll just open the folder where I'm keeping my stuff. Okay, so my stuff is in this folder, March 23, and this folder is in RGIS folder. Then there's another folder, seminars, and it's in documents, or just go on documents, seminars, RGIS, March 23. So this is my working directory. So I have my scripts here, and I have